Okay, good morning, everybody. So I understand today is the deadline for test number one. Is that correct? Just kindly check your CASA calendars, but I hope you guys had a good time preparing for the exam. Uh, okay, as I was saying, hello, good morning. Hi, everybody. Can you hear me now again? I think there's some sort of a glitch. I am I'm getting muted from time to time. But anyway, I hope it's better now. So as I was saying, I hope your preparations for test number one is going well or did went well if you already took the exam. What I'll do is just to know how well you did in the exam, I'll post a poll in the lab meeting channel, and please just put there your score. It would be an anonymous poll so that you won't your scores will not be broadcasted to everybody. But yeah, just to give me a rough idea of how you are doing in the exams, right? And then today we'll continue on tackling some examples for computing areas. What did you do in the lecture today? Did have you started with using integrals in computing volumes?
Yeah, that's what we went over today.
Mm-hmm. And I'm feeling that it is a little bit too fast for me. Yeah, when I was teaching this course before, it took me a couple of days to finish computing areas, then another couple of days for computing volumes. But anyway, maybe that's the point of having the labs so that we can answer more examples. But let's focus today on computing areas and let's see if we can go over computing volumes. So for computing areas, as we have discussed last meeting, it's about setting up the integral, right? But in order to set up the integral, you should have a good idea of how the graphs of the function look like, right? Or how the shaded region will look like. So that's the first step. Have a good idea of how the function or how the region looks like. So what is the function on top, on the bottom, what's on the right, what's on the left. So for instance, you figure out the shaded region to be the one here highlighted in yellow, and then you decided to use vertical strips. Remember that vertical strips should always be used with a variable x. So when you decided, oh, I'm going to use vertical strips, write that dx over there, just to remind you that your integral would be with respect to x. Then after that, you need the bounds for x. Now the bounds for x, from what x value does the region start and when will it end? So based on this drawing, the graph, the region starts at a and ends at x equals b. That's why I had the bounds a and b for the integral. And vertical strip and the integrand would be the length of the vertical strip. And how to compute the length of the vertical strip? It's the function on top minus the function on the bottom. That's why it's important to get a good picture of the shaded region. So in this case, the upper function is the red one, which is f of x. The lower function is the blue one, g of x. So the integrand looks like f of x minus g of x, right? Okay. Instances wherein using horizontal strips might be more advantageous. So for instance, here I have the graph here, and say I decided to use y. I use horizontal strips. So when you use horizontal strips, the variable of integration should be y. So that means you should have a dy. And then once you have a dy, hold on, I'm getting notifications, but I'm not seeing your replies. Oh, it's about bonuses. Okay, now going back. Yeah. Horizontal strips always go with dy, so put the dy over there as a reminder that the next step would be to bound your integral by values of y. So you look at what is the y starting value for the region and what is the y ending value. So according to the picture, the starting is c, the ending is d. So I have those two bounds. And then the integrand would be the width of the horizontal strip. Now the width strip is the function on the right minus the function on the left. So that's why I have f of y minus g of y over here. And remember, this is dy, so the integrand should have the variable y in it. Okay. Now I guess we finished one example last time, which is finding the area of an obscure looking triangle on the Cartesian plane. And I guess we uh, we found the solution to be quite simple as long as you remember some things from your pre-calculus or algebra classes, specifically finding the equation of a line. Okay. Now we moved on and look at example number 2. But as I mentioned last time, the graph of the second function, y equals 5x minus x cubed, is a little bit difficult to imagine without using any sophisticated technique. Because remember, the first step in getting the area of a region using integrals is to have a good picture of how the graph look like or how the shaded region looks like, right? So here I use some tricks from Cal 1. I think I started with using the first derivative to determine when is the function increasing or decreasing. And then I used the second derivative in order to find when is the function concave up and concave down. So I will not go over the details again. I included it in the annotated worksheet that I uploaded last Wednesday. Just let me know if you have specific questions on this. But other than that, I'll assume that you know how to come up with the graph of the region. All right. Now, we were told to find the area of the region bounded by the two curves, y equals x and y equals 5x minus x cubed. When we say bounded or the region bounded, that should be a region that is totally enclosed. So it should not go to infinity. So all of the parts of the region that is completely enclosed by the two curves is considered to be shaded, right? So what I mean is the shaded region here would be this and these two regions over here. Well, this part over here is not bounded by the two curves because it will go indefinitely to the right. So it's not a bounded region. It's not a totally bounded or totally enclosed region. So hence that will not be included in our calculations. So the area that we need to compute would be that of the region highlighted in yellow, right? And then here I will decide to use vertical strips, and I will tell you later why I feel it's more convenient to use vertical strips than horizontal strips here. Because what I'll do is, okay, I'll draw a vertical strip over here. And remember, the integrand depends on the height of this vertical strip. So it's top minus bottom. So if my vertical strip is located here, then the top function will be the blue one and the bottom function will be the red one. However, when I draw a vertical strip over here, all right, the top function is the red one and the bottom function is the blue one. So that tells me that I cannot solve the area of this region using only one integral. Because remember, it's top minus bottom. But unfortunately, there are some portions of the region wherein the top function is the blue one and the bottom function is the red one. And on other portions, it's the other way around. So that tells me I need to divide the integral into two pieces. The first piece having the blue on top and the red at the bottom, and the second piece an integral wherein the top is the red one and the bottom function is the blue one, right? And how do I find that? Well, that's a good question, Muriel. Wouldn't they cancel out since the areas are symmetrical, but one is negative and the other is positive? Good question. If you're talking about integrals, right? So if you're integrating a function that is odd, that means the integrals will cancel each other. But remember, when working with areas, we assume them to be positive quantities. So basically, the area that will be coming off from the integral evaluated in this portion, let's call this area 1, that will be positive. Okay, because though the region is at the bottom of is below the x-axis, so the integral understandably would be negative or can be negative there, but we're talking about areas, and areas are assumed to be positive quantities. So basically what we consider in area 1 would be a positive number. Yes, I can do that. Solve for only one and multiply it by two. But the problem with that is I want to be a little bit careful because I'm not sure yet if they are really symmetrical. So I need to do some tests from algebra to verify that indeed they are symmetrical. Based on the picture or based on intuition, they might look very symmetrical, but I'm not sure for certain. That's why I will do it carefully using calculus techniques. But if you remember some tricks from algebra to be able to show that this is indeed an even function or an odd function, or to show that indeed they are symmetrical, then go ahead. You can solve for one integral and multiply it by two. But the problem with that, again, I'm not sure that they are indeed symmetrical. So I will not assume that you know the algebra, the tools from algebra that is required to show that they are really indeed symmetrical. So I'll go ahead and do it the calculus way. So, but you're free to use algebra tools, though they are not required here. And if that pans out to be also true, then we should come up with the same answer. All right. Okay, so let me do it the calculus way. So I'll compute for the area. Oh, but before I can compute the area, remember I decided that I'm gonna split the integral into two pieces, and that will require me to know when will the top and the bottom function interchange with each other. And more importantly, I should know when does the functions, the region start and when will it end, right? Because I need those at the bounds. Well, the here, and then it ends here, though I have a good idea that this would be 0. And then here, and then the second area would end here. But those are basically the points of intersection of the two curves. So after you have a good idea of how the graph looks like, you will realize the need to find the points of intersection. So that would be the next step. Solve for the points of intersection. So I'll use POI here for points of intersection. So our first step is to sketch the graph. Next is solve for the points of intersection whenever they are not obvious. And how do you solve for the points of intersection? Just equate the two functions together. Remember, we have the first function is y equals x. The other function is 5x minus x cubed. And then we solve for the x's when these two values are equal to each other. So basically, I'll have x cubed minus 4x equals 0. And then I can factor this into x times x squared minus 4 equals 0. And then essentially, I'll have x equals 0 or x squared minus 4 equals 0. So x is equal to plus or minus 2. So the points of intersection happen when x is equal to 0 or plus or minus 2. So this is, it turns out this is minus 2. Then that's 0. And then this is equal to 2, right? And we notice that the first area that ranges from x equals -2 until 0 has the blue function on top and the red function at the bottom. So that means the area will be given first by the integral from -2 to 0 of the top function is x minus the lower function, which is the cubic one, 5x minus x cubed dx, plus the area of the other region, or the other subregion, starting from 0, ending at x equals 2. If you remember, the top function is the red one, which is the cubic. So I'll have 5x minus x cubed minus the blue function, which is x dx. All right. Is that good, guys? All right. Okay, I'll take that as a yes. And then all you need to do is to evaluate this integral. Simplify the integrand first and then carry out the integration. Will it be okay if I leave the integration to you guys? Basically, if you do the calculations, this would be 4 plus 4 equals 8. And it turns out that Muriel's suggestion earlier might work because I'm looking at these two answers here, and it seems that indeed they are symmetric. Region 1 has area 4, region 2 has an area 4, so the total would be 8. But again, the only uh, my only reservation with that suggestion is that I am not sure for certain that indeed the two regions are symmetric. But looking at these results, it seems that they are. But if I will be answering this, I will not bet on them being symmetric unless I do some algebra tests. Okay? All right. So you have a question, Kingsley?
Yeah. So you said you're not certain because the graph was kind of weird. So it's 5x minus x cubed, and we don't really know how to graph it. So that's the
Yeah,
reason why you're not
right.
sure
If
that.
it, mhm.
Yeah.
Yeah, if it was just y equals x cubed, then I'm sure there's some sort of symmetry.
Yeah.
Then I'm fine using the trick of just solving for half and then multiply it by 2. But 5x minus x cubed to me is not clear if it's symmetric at all. So I'm just being extra careful. But for those basic graphs, you can use the symmetry without doing any other tests.
Okay. Yeah, that makes sense.
All right. So why did I say that? Okay, just another point here. Why did I say that using vertical strips here would be a little bit more convenient than using horizontal strips? The reason is that if you will use horizontal strips, if you draw a horizontal strip over here, this would be red minus red, or the right portion of the red minus the left portion of the red. Over here, a horizontal strip will have right boundary the red function and the left boundary the blue one. Then over here, you will have a blue on the right, a red on the left. And then here, you will have a portion of the red and another portion of the red on the left. So that means how many integrals should I compute? I need to compute 4 integrals, which would be a lot messier than what we have done with vertical strips. So basically, if you have the option, you can imagine drawing vertical and horizontal strips all over the region, and the less number of splitting of the integral or of the region would be the more better or the more convenient choice. Okay. Right. So let me see. I'm picking some problems from the worksheet. You can request if you have some specific problems you think from the worksheet that we should answer. Though I selected some, and I think they better summarize the topic. But don't worry, I will complete the solution to the entire worksheet. So just wait until the end of the day. I will upload a complete solution to everything here in the worksheet so that you can have something to review. But let me just discuss the more interesting ones. So let me see what would be good. Maybe I'll try problem number 5, if that's fine with you guys. So for problem number 5, let me see. What was problem number 5? I forgot to open my other copy. Okay, for problem number 5, we are asked to find the area of the region bounded by, let me call the region R, bounded by y equals x cubed and y equals 4 root of 2x. Okay. Now, again, first step is to sketch a graph. Okay, so we sketch the region by sketching both graphs and then see if we can deduce some information from it. Okay, x, y. Y equals x cubed, that's fine. I don't need any calculus 1 technique to know that the graph will look like this. Y equals x cubed. Then let's use another color for y equals 4 times root of 2x. Well, it's a square root function, so it's the upper semiparabola opening to the right. So when x is 0, the second function will have y equals 0. And then when I have 1, so say here is 1, here is 1 as well. And then if x is equal to 1, then on the second function, I will have what? Oh, 1 is not a good choice. Maybe I should have 4. Oh, sorry, 2. I'll use x equals 2, plug it in into the second function. I think I'll have 8. So figure not drawn to scale. So this would be our region, the second graph. So this is y equals 4 root of 2x. All right, so here I only needed to have an idea of how the graph looks like. I know a square root function is a semi-parabola, so it either opens to the left or to the right, and then take half of that parabola, and then I just give two specific points. So this is my shaded region. Let me shade it by yellow, and I want to get its area, okay? Now let's try using both strips. But before that, I need to find the points of intersection, right? Or let me complete this. I'll need to solve for the points of intersection. And again, I can do that by simply equating the two functions together. So I have y equals x cubed. Then I have y equals 4 root of 2x. And then what can I do here? I can get rid of the square root first by squaring both sides. So I'll have x to the 6th equals 4 um, times 2x. So I'll have x to the 6th equals 8x. Oh, sorry, not 8. I have 16. So you know it's already Friday when my math is not working. Yeah, it's not working optimally at all. So 32x, I think that's fine. And then we can collect all terms to one side. So we'll have this and then factor. I'll have x times x to the 5th minus 32 equals 0. And then that means x equals 0 or x to the 5th minus 32 equals 0. Okay. And then that means x to the 5th equals 32. Take the 5th root of both sides will give us x equals 2. So that means this is 0. And then this is, actually, this point of intersection here would be 2. That's why I need to adjust my graph. Oops. All right. Okay, thank you, Muriel. You caught that. All right, so now we know the points of intersection. And then let's try setting up the area using integrals. Well, I can use let's try using a vertical strip. Okay. If I'll use a vertical strip, so I drew a vertical strip over here. Imagine the vertical strip being moved to the left and to the right. As I go along the interval 0 to 2, I see that the function on top is always the red one, and the function at the bottom is always the black one. So that means I don't need to split the integral into two pieces anymore. I can do it in just one shot, right? So the top function is the square root function, and the bottom function is the cubic function. And I know that the region goes from x equals 0 to x equals 2. So here I can write my solution using vertical strips. Again, for vertical strips, you always have a dx. And then since we have a dx, we need a bounds for x. But we knew that x starts when at the point of intersection and ends at the other point of intersection, and they are 0 and 2 respectively. And then the top function is the square root function minus the cubic function, which is at the bottom. So that would be the integral that will give you the area of the shaded region. If you calculate this, this will be, I hope this is right, 20 over 3. So I hope you can integrate this properly. This is just an application of the power rule, right? And then let's try horizontal strips for a change. Well, let's see if the horizontal strips will be as convenient as vertical strips. Now, if I'll draw a horizontal strip, then this will go that way, right? And imagine that horizontal strip being slid up and down the region. And you see that no matter where I place that horizontal strip, the black function will still be on the right and the red function will remain on the left. So again, horizontal strips will not require me to split the integral up. So that means it's as convenient as using um, vertical strips. So my area here will then be an integral with respect to y. And then I need to bound the y, right? Or the y values. Well, from the picture, I know that the graph starts at y equals 0. And remember, the point of intersection is when x is equal to 2. But when x is equal to 2, I know that the y values of both functions would be equal to 8. So I know that the region starts at y equals 0 and ends at y equals 8. So my bounds here would be from 0 until 8. So notice the very distinct way of setting this integrals up. dx bound the x values. dy, you need to bound the y values, right? But remember here, my variable is y. So my functions should be expressed in terms of y. So what is the right function? The right function is the cubic function, right? So remember the cubic function is y equals x cubed, but the integral calls for something that involves only the variable y. So here I need to solve for x in terms of y, but that's fine. I can simply take the cube root of both sides to get x equals cube root of y. And so that will be my minuend here, cube root of y minus the right function. The right function is the red function. Remember from our sketch from above. So we know that the equation for that red function is 4 root of 2x. But since I'm using dy, I need the function to be expressed in terms of y. So here I need to solve for x in terms of y. To do so, I'll first want to get rid of the square root. So I'll square both sides. So I'll have 16 times 2x again. And then I'll solve for x. This means that x is equal to y squared over 32. Okay? And that's what will be in my integrand as subtrahend. So y squared over 32 dy, right? And if you try to evaluate this integral, you will also get 20 over 3. So it doesn't matter which strip you will use, then you will end up with the same answer. Nadia, how do I get the 8? Well, remember that here dy, I need the bounds for y, right? So I'm going to look for the bounds for y here, back at the region. I know that the region starts at x equals 0 and ends when x is equal to 2, right? But I need the y component. So if x is equal to 2 here, so x equals 2, then what would be y? I can plug in into either this equation or this equation because they both share this y value, right? So I'll choose the easy one. I'll plug in into y equals x cubed. So I'll have 2 cubed. That's why I knew that when x is equal to 2, the y value is equal to 8. And that's the upper bound. You could have decided to plug in x equals 2 into the red function because anyway, the red and the black function intersect at x equals 2, which turns out to have a y value equal to 8. Okay? All right, yeah. Other questions? Let me see. Yeah, if it's with respect to y, Arsalan, I do right minus left. Okay. So if it's dx top minus bottom, if it's uh, dy, then you do right minus left. Okay. Is that good? Let's see other examples. All right, let me see. What would be an interesting one? Okay, let's try problem 7. Okay, for problem 7, the functions that will bound the region are the following: 4 minus 3x and y equals e raised to x on the interval -1 to 0, right? So sometimes you will be given problems like this that given just the two functions alone, they will not give you a bounded region or a completely enclosed region, but you will be given a restriction on the boundary on the interval. So that will also be fine. Now let's see. Okay, let's sketch the region then. So maybe I should put here. First step, sketch the graph. One of the comments I received in the poll that I have uploaded is that they say that sometimes my handwriting is hard to read. Um, I don't know how I can improve on that, but anyway, I hope you will grow into it. Usually, I speak what I write, so just take note. And if there's something that you cannot read, just let me know. Okay, so especially when doing quick writing, my tendency is to write like a doctor. So yeah. Okay, let's sketch first the linear function. So the first is the linear function, y equals 4 minus 3x. It's a line, so I simply need to get 2 points. So when x is equal to 0, then y is equal to what? Y will be equal to 4. So let's put 4 over here. X is 0, so that's my first point. And then maybe I'll start with -1 because we were told that the region will start from -1 until 0. So I'll put x equals -1. That would give me 4 minus -3. That would be 7. Okay, so 7 could be here. Again, my figures are not to scale, so that's why I'm labeling them with numbers. Okay. So here would be y equals 4 minus 3x. And then let's plot e to the y equals e to the x. Well, when let's use blue one here. So for y equals e to the x, if x is equal to 0, then y is equal to 1. So let's put 1 over here. And then if x is equal to -1, then y is equal to 1 over e. Remember, e is 2.71 something, but it is, so definitely it's less than 1. So let's say 1 is here, and then 1 over e is here. Okay. And then I'll connect it into a graph that looks like e to the x. Okay. And then we were told to only find the region from -1 until 0. So my shaded region looks like this. Okay, based on this picture, I will not attempt to use horizontal strips. Why? Because if I'll do horizontal strips, I need to have an integral here because that will be red minus black. Here it would be x equals 0 minus x equals -1. And here it would be blue minus red. Sorry, blue minus black. So that means I will need 3 integrals in order to evaluate uh, the area of the shaded region if I am to use horizontal strips. But if I will use vertical strips, if I will slide this to the left and to the right, I will always have the red function on top and the blue function at the bottom. So no need to split the integral up. So here, I will compute the area using vertical strips. Vertical strips are always associated with dx, so I'll have a dx over there. And then the bounds would be bounds for x. The region starts when x is -1. The region ends when x is equal to 0, right? And then the integrand would be top function, 4 minus 3x, minus the bottom function, e to the x, right? And when you evaluate this, you should get 9 halves plus e to the -1. Oh, this is 9 halves, not 9 over e. Okay, any questions for this? You're too quiet in the chat. Any question? Now, I have a question for you, Dan. Are these examples enough for computing areas, or do you want to go ahead and tackle computing volumes?
I wanted to see one whenever we do horizontal, whenever we do it like with the y integration, and it's bound to itself. So like you know how whenever you're saying it's gonna be bound to -1 and then the 4 minus 3x. Well, I wanted to see one where it's like a parabola and you have to bound it to itself.
Okay, yeah, that sounds good. Let me see. What example do I have on that? Probably example number probably example number 3. And then I will show you how to solve it both ways. So when x okay, for number 3, f of x. Yeah, Daryl, they are right. If you will use horizontal strips, so you will have right minus left, okay? But the right function and the left function changes more often than once in the shaded region. So you will have 3 integrals to do that. Okay. So for example number 3, you have x squared minus 4x, and what is the line? I guess the line is f of x equals negative x plus 4. All right. Let's start with sketching the region. Okay. Now the first one is a parabola. Oops. The first one is a parabola. Let's start with that. Okay, so I'll have y equals x squared minus 4x. The vertex occurs at x equals negative b over 2a, b being the coefficient of x, so that's negative 4 in this case. And then a is the coefficient of x squared, which is 1. So that means the vertex occurs when x is equal to 2. Right, so if you remember from algebra, the vertex is almost always the most important point in the parabola, at least insofar as sketching its graph is concerned, because that's the best way to start. And if x is equal to 2, then y is equal to 2 squared minus 8, so that would be negative 4. So the vertex is over here. Then all I need to do is to give 2 values, one from the left and one from the right of the vertex. So if I'll try x equals 0, then that means y is equal to 0. I'll have a point here. And then if x is equal to 2, I know that the value, x equals 4, I know that the value is also 0, because the parabola is supposed to be symmetric along the vertex, right? So if I go 2 units to the left, that gave me y equals 0. If I go 2 units to the right, that 4, that will also give me the same value. Again, using the symmetry. But in case you forgot the symmetry argument, then you could have just chosen any number to the right and any number to the left of the vertex. Compute the y values, then you should be fine, right? So this is the parabola, y equals x squared minus 4x. And then for the line, I'll just need the 2 points. So the second function is y equals negative x plus 4. Any 2 points will do. Say x equals 0. That will give me y equals 4. That means here x equals 0, y equals 4. And then say if x is 4, then I'll get y equals 0. Okay. And it just so happened that I was very lucky to already get one of the points of intersection by just picking the right point, right? So the shaded region looks like this. Okay. But in order to characterize the integral, I need, or the area using integrals, I need to find the points of intersection because they will be the boundaries for the integral. So here, I need the point of intersection there. We already know one, that is x equals 4, but let's compute for the other. So to solve for the points of intersection, so sometimes the POI can appear directly once you graph, when you sketch the region. Just like what happened here, I know there's a point of intersection when x equals 4, but sometimes you really need to do the algebraic solution to find the points of intersection. Usually it's not a big deal. You simply equate the two equations together. So the parabola equals the line, okay? And then we'll have x squared minus 3x minus 4 equals 0. And then we factor, we'll get x minus 4, x plus 1 equals 0. That means x is negative 1 and 4, right? So that means this point of intersection here is x equals negative 1, okay? So now if we will have, if we will use vertical strips, right? So again, this is integral with respect to x because it's vertical strips, right? And if I draw a vertical strip here, I slide it to the left and to the right. Anywhere inside the region, the top is always the blue function and the bottom is always the red function. So no need to split the integral. And we knew that x starts at negative 1 and ends at 4. So those would be my boundaries, negative 1 to 4 of the top function, which is the line, negative 4x, negative x plus 4, minus the parabola, which is the lower function, that's x squared minus 4x. So be careful with the grouping symbols here. You want the entire lower function to be the subtrahend. So minus, then grouping symbol, put the terms of your, or put the expression for the second function, right? So be careful with the grouping symbols there. And when you perform the integration here, you should get 125 over 6, right? Now, one of your classmates asked, how about if I use horizontal, use horizontal strips? Okay, let's see. If I will do horizontal strips, I know that the area should be expressed in terms of the variable y. Okay, now that means we need to compute for y in terms x in terms of y. So we know that for the parabola, we know that y is equal to x squared minus 4x, right? But here I need to solve for x in terms of y. So that means here I need to do completing the square. So this would be y. I will add what? I will add 4 to both sides equals x squared minus 4x plus 4. And then y plus 4 equals x minus 2 quantity squared. Then I take the square root of both sides. So I'll have plus or minus y plus 4 equals x minus 2. Then I'll add 2 to both sides. Then flip the equation. I'll get 2 plus or minus root of y plus 4. Okay. And this is what happens. You have two options. Remember the graph of the parabola looks like this? Yeah, that's why here I wouldn't suggest you use horizontal strips. It's just one of your classmates would like to know what will happen if you have a parabola minus another a part of the parabola, right? So what happens here is that here we see that the function has two options, 2 plus root of y plus 4 or 2 minus root of y plus 4. So that means, that tells us that here at the vertex, where was the vertex again? The vertex is at x equals 2. The right portion corresponds to 2 plus root of y plus 4. And the left portion corresponds to 2 minus root of y plus 4. Okay. And then remember the graph is, we have a, the other graph is the line that goes like that, right? Okay. Now, in this particular case, if you insist on using horizontal strips, you see that at this portion, the horizontal strip will require you to have the right parabola minus the left parabola, but above you will need the line minus the left parabola. So that means here, oh, I forgot to solve for the equation of the line in terms of in terms of y. So remember, for the line we have y equals negative x plus 4. So that means I'll have y minus 4 equals negative x. So x will be 4 minus y. Okay? And then what are the points of intersection? Here we know that this is what? 4 comma 0. And this one is, what was the y value there? The other point of intersection is at x equals negative 1. If I plug it into either equation, I will see that this is 5, right? So when x is negative 1, y in either of the two graphs will be equal to 5. And when do we have a parabola minus a parabola? So we have it from here. Or actually, the region starts here. All right, let me just pull it up. So this is our shaded region. It starts where? With respect to y. It starts with the vertex, right? That's the lowest point of the region, the vertex. And we knew that the vertex occurred when x is equal to 2. But when x is equal to 2, what is the y value? So we'll have 4 minus 8. I guess we have negative 4. I plug it into the parabola. I guess I solved that earlier. Yeah, x equals 2, yeah, negative 4. So we have it at negative 4 there. So then the integral would be what? We'll start from negative 4, okay, which is over here, until the point that we have a parabola minus parabola. The last would be here, right? Until 0. Starting from y equals negative 4 until y equals 0, we'll have a right parabola minus the left parabola. So that would be negative 4 to 0 of right parabola. The right parabola is 2 plus root of y plus 4 minus the left parabola. I'll need to be careful and close the subtrahend inside a grouping symbol, y plus 4 dy, right? And note that they won't cancel each other out, because when you distribute it, it will be what? Twice of root of y plus 4, right? Which makes sense because it would be symmetric with respect to the vertex. So what you could have done is just compute half of the area, then multiply it by 2. But anyway, and then the last portion would be from 0 until, what's the ending y value? The region stops at y equals 5. So that would be my upper bound. And then I'll have right. The right function is the blue one. That's 4 minus y. Minus, I'll have what? I have the left parabola. And the left parabola is 2 minus root of y plus 4 dy. And if you calculate this, you're guaranteed to have the same answer, 125 over 6. But you see, it's much more involved and much more much more messy than the one using vertical strips. So sometimes it really boils down to first choosing the right kind of strip, or the easier strip. In exams, um, it's kind of a mix type of problem. Sometimes you will be told to use vertical strips right away. Sometimes you will be told to use horizontal strips, or you will be told to do both. But there are also some instances that the choice is left to you. So, but I don't think it's a big deal. You just try to draw a horizontal strip, slide it up and down, and see if there's a change in the right and the left function. The same for vertical strips. So the option would be yours. But I guess there are some parts of the exam, especially when you go to double integrals in Cal 3, that you need to switch between the two variables. So yeah. Okay, any questions with this one? Right, it's already 10 minutes before the time, but if you guys don't mind, I'll stay for another 4 minutes to answer Michael's question. Uh, hmm. Okay, quickly, explain the integration for vertical strips. The integration for vertical strips is just top minus bottom, right? So if you look at the region, oops, okay. So the region started when x is equal to -1 and ends when x is equal to 4, right? That's why I have those bounds. And then if I draw a vertical strip such as this, the upper function is always the blue one, which is the straight line, whose equation is -x plus 4. That's why I have that as a minuend, minus the lower function. The lower function is always the red one, which is the parabola. So that's why I have minus the equation of the parabola dx. And when you do the integration, I guess that's straightforward. You should get 125/6. Okay, does that make sense, Daryl? Okay, there's an additional question from Michael. Let's just do this quickly. If you do have classes, you are free to go, guys. I'll just finish this one up. You can watch this portion of the recording later if you need to go. Let's call it additional example A. So here you have the region R is bounded by the x-axis, y equals 2 sine x and 2 cosine x, where x is where x is an element of 0 to pi/3. Okay. All right, so first sketch the graph. So let's see. The good thing here is that we are only concerned with the region starting from x equals 0 until x equals pi/3. Okay. So when x is 0, I'll start with the sine function. When x is 0, sine is 0, so I'll have here. And then when x is equal to pi/3, what happens to sine? Sine of pi/3 is √3/2, right? Okay, so this is the graph of y equals 2, or actually there's a multiplier 2, so that should be √3, right? I forgot to multiply it by 2 because our function is 2 sine x, right? So, okay, that's the portion of the sine curve. If you want to continue, the sine curve will look like something like this, right? All throughout the interval, but no need for the entire graph. I'm only interested from 0 until pi/3, right? And then I'll go with a cosine. Cosine of 0 is 1 times 2, so that means 2 could be here. And then what is cosine of pi/3? Cosine of pi/3 is Cosine of pi over 3, isn't it equal to 1/2? Times 2, that will be 1, and 1 is over here. So I'll have this. Yeah, so that would be y equals 2 cosine x, right? Yeah, is that right, Joseph? Yeah, cosine of pi over 3 is 1/2 times 2, so I get 1. So the shaded region is this, this and this, right? Because we're looking at the region bounded by the two curves over 0 to, sorry, let me see, the x-axis. The problem says it's bounded by the x-axis and the two curves. Yeah, I'm thinking about that, Muriel. Yeah, if this is indeed the shaded region, then it would be an integral will with 2 cosine x minus 2 sine x, and then another integral with 2 sine x minus 2 cosine x. But I forgot this condition, that the region R is bounded by the x-axis and the two curves. Let me just reread the problem. So it looks like that the shaded region should be this. So that's one important thing. We need to be careful how to interpret the shaded region. Do you agree, guys? This should be my shaded region. Though the question is a little vague for me because it says that the region is bounded by the x-axis, y equals 2 sine x, and y equals 2 cosine x. There is no common region that is being bounded by all three of them at the same time, because this portion of the region is only bounded by the x-axis and the sine function. This part of the region is only bounded by the x-axis and the cosine function. So that's why this shaded region is a little bit vague to me. But if that's the case, then if we accept that this would be our shaded region, okay, then I still need to split the integral up into two pieces. All right. Okay. And you need to look for the point of intersection here. And then do two integrals. The first integral is 2 sine x minus 0, because the equation of the x-axis is y equals 0. And you'll have 2 cosine x minus 0, because that's the equation of the y value of the x-axis. Well, that was the first thing that came to my mind, Harrison, because that is the typical question. But I have this restriction that the graph is bounded by the x-axis. That's the one that bothers me. All right. So that means the x-axis, which is over here, should be involved in the bounding of the region. So yeah. Okay, unfortunately, I have another class starting at 12. I'm a little bit late on that. Yeah, but I hope that helps, though this problem is a little bit tricky and it's a little bit vague for me. So yeah. But the idea is the same. It's a top region minus the bottom region, top function minus the bottom function. All right. So I'll just upload the this annotated worksheets along with the answers to the rest of the problems we didn't cover. A detailed solution expected to be up later in the day, and then we'll start hopefully on Monday with some examples for volumes. All right. And plus your questions about areas if you still have some. All right, guys. So thank you for coming. Have a good weekend. See you again on Monday. Bye.